Hello and welcome to our second lecture in our online lecture series of metrics for Colgate University 2020. What we're going to be talking about today is more information about instrument variables. In particular, we're going to be looking at what happens when those assumptions that are necessary, the inclusion criteria and exclusion criteria, don't apply. Let's quickly go ahead and review here. And review what exactly instrument variables are. So just making a quick example. What we're doing with instrument variables is we're separating out our X into two components, one that is probably correlated with the error term and one that is not. Now, we've talked about this semester the problems measuring office hours and how attendance at office hours impacts your grade. And we said that's problematic to look at and figure out because there are probably other things like whether you actually read the textbook, whether you do the labs and the homework that impact grade but are correlated with your office hours. And so if we're simply looking at the impact of office hours and your attendance there, we're probably going to get a biased estimate because of this connection between the other stuff that impacts your grade in office hours. Now, we're doing these courses fully online, and some of you have really good internet connections, which is great, and some of you do not. Now, this could be a potential impact of your ability to attend office hours, whether you have internet. And what we would expect is that whether or not you have internet would impact office hours, but wouldn't independently impact grade. So it's not, for example, it's not in the error term. It is separate from the error term, but it does impact office hours. And we can write this out very quickly mathematically. What we're going to do in our two-stage least squared method here is first we're going to say, how is office hours impacted? How is office hours impacted by internet? And it'll explain a portion, but we'll also have the other things that still exist. And we term this the predicted amount of office hours that depends on this exogenous portion, whether you have internet. We term this office hours hat. This is our first stage. Our second stage, what we will do is take that predicted value for office hours and use it in our regression. So grade is our Y variable. And now we're going to use office hours hat as our X variable. And I just want to emphasize putting the prime there that our error term has changed because our error term now includes our previous error term and also the unexplained portion of office hours. We're now just leaving that out and leaving it to the error term. So that's an example by way of review. What we want to talk about today is what happens when these two conditions, which are the necessary conditions to do our two-stage least squared regression, what happens when they don't apply. So the first condition here is our inclusion condition. What we have is that the covariance between Z and X needs to not be 0. So does having internet really impact office hours? That's the question we're asking. And if office hours are done online only, and not having good internet means that you can't do a synchronous chat over video, then yes, we would expect that there would be an impact between having internet and office hours. So in our example, we might expect it to apply. The exclusion restriction is, does internet impact grades in other ways? So other than having an impact through office hours, does having impact, does having internet impact grades? This is saying, is internet part of or related to the error term? So if students actually do a decent amount of Google searches and reading online to learn about the course material, then this would fail. Then this would not hold. This exclusion criteria would potentially be violated. So let's talk first about the first one. When this fails, it doesn't usually fail completely. It's not that the covariance of Z and X is completely 0. But what we're actually interested here in is talking about the strength of the instrument is what we'll term it. How big of an impact is our potential instrument? Now let's go back to our diagram briefly here, where we have our Z, which is our instrument, impacting our X variable and separating it out into 2 components. A strong instrument does a very good job of explaining X. It has a big impact on X. A weak instrument maybe explains some of X, but explains a very small portion. And you can see with this diagram here that I've made these connections very small. And what you should think about it that is that if we have a very small connection between Z and X, it's going to be very hard to detect and show X's effect on Y, because we're not going to be left with a lot of variation that we can explain. We're just not going to be very clear to having the impact. Another example I've used as an instrument is sort of your proximity to, if you're living on campus back when that was a thing, your proximity to office hours. If that's not a particularly big factor in the decision to attend, then potentially using that as an instrument doesn't give us a lot of variation and information about whether you attend office hours. So what we would talk about here is the strength of the instrument. And in particular, if we have a very strong, low correlation between X and Z, we call it a weak instrument. And in our next lecture, when we talk about the variance of our estimator, the variance of our two-stage least squares beta hat, this will come into play and become a little bit more clear. The next way that this can fail is First, we talked about the inclusion restriction. The next way that this could fail is the exclusion condition. So the exclusion condition is that the error term needs to be independent of our instrument. So it could be that it's not completely zero, but it's small. So we're not quite exogenous, but there's a small impact. Maybe sort of the ability to search for things online is not a huge impact, but it is a part of the error term. And so in terms of this design, maybe there's still some little connection here between the error term and our new x. So the definition of an instrument here, we need to satisfy both the inclusion restrictions and the inclusion restrictions. What we're doing here, what if this is not zero, and if it's only close, is we're actually technically almost an instrument, but not quite. And so what we term this is a quasi instrument. It's almost an instrument, but not close, not quite. It's very close, but not quite. What that means then is we're actually going to have still some bias. And so our OLS will give us a bias estimate. Our two-stage least squares also will give us a bias estimate. And we need to think carefully about, is it worth it to do two-stage least squares? So if we look at how the probability limit, now there's certain mathematical reasons that we're going to look at probability limits rather than expectation, which I'm not going to get into here. But if we look at how the probability limit differs for beta hat in OLS to that real thing, now this idea is very, very similar to the idea of bias. This is just going to be the correlation with the error term and x1 times the standard deviation of the error term over x1, standard deviation of x1. And if we look at the plim for the probability limit, or plim, for beta hat in the instrument variable case, and how that differs from the true value, what we have is something very similar. It's the correlation between the error term and z. Now I'm going to throw something else in there in a second. Divided by the correlation between c and x. Now, if we look at how these things matter, if we have a true instrument, then this is going to be unbiased because this is going to be equal to 0. If we have a true instrument, then the expectation of the error term given z is 0. So there's no correlation between those two. So that would be 0. Secondly, the other thing to notice is that what we have is the correlation between z and x. If this is 1, then these look exactly the same. If z is actually x, then these equations are exactly the same. If we have a very low correlation, if we have a weak instrument, then this will be bigger. than our bias that we're getting from our instrument variable, or the difference between the probability limit is going to be higher. And so what we're actually going to have to do when we're thinking about these things, now again, we're talking about the error term here. So we're not going to necessarily be looking at these in data, but as we're thinking about how this is going to work, we can actually look at the correlation between Z and X in data. Is we can say, let's compare the correlation between Z and X versus the correlation between the error term and Z, and the correlation between the error term and X. So what we have on the right-hand side is how much are we reducing our bias by? How much are we reducing that? Are we cutting it in half? Are we cutting it in a quarter? Maybe we can kind of get a ballpark guesstimate of that versus how much the correlation is between Z and X. If the correlation between Z and X is high, we're going to prefer our two-stage least squares. So if this is greater than that, then use two-stage least squares. But if we have both a weak instrument, meaning small correlation, and we don't have a very, we have a stronger correlation between E and Z, if those things are happening, then we're going to want to use OLS. So I'm going to stop there for today for this lecture. Next up, we'll be talking about the variance of the estimator for IV and how that compares, as well as looking at trade-offs between bias and variance. I hope you are all well, and I hope to interact with you soon. Bye.